Hello YouTube! In this video I want to present an interesting view defended by John Norton, the material theory of induction. In a nutshell, the material theory claims that there are no rules of induction, that all inductive inferences are warranted by specific facts, not by rules. So let's explore this in a bit more detail. Broadly speaking, we can distinguish between two types of inference. On the one hand, there is deduction. So in deductive inference, the truth of the premises guarantees the truth of the conclusion. Philosophers have found various schemas or rules for deductive inference. For example, all A are B, all C are A, all C are B. All men are mortal, all Greeks are men, therefore all Greeks are mortal. This is familiar stuff. You can find lots of different schemas for inductive inference. Now, deduction is purely formal. With a valid deductive form, we can substitute any concepts we like for A, B, C, whatever, and the resulting argument will still be valid. Deductive inferences hold universally. The reliability of deduction is not dependent on facts about the world. So no matter what the world is like, and no matter what we substitute for A, B, C, it would be impossible in these cases for the premises to be true and the conclusion false. So, if the moon is made of cheese, then the moon is edible. The moon is made of cheese, therefore the moon is edible. Well, that's a bad argument, but it's a valid argument. Under the assumption that the premises are true, we can see that the conclusion must be true as well. There could be no world in which the premises were true, but the conclusion false. And the reason for this is that deduction is conservative. In a valid deductive argument, the conclusion doesn't tell us anything more than what we are told by the premises. It's simply a matter of revealing content that the premises already contain. To say that all men are mortal and that all Greeks are men, that already contains the information that all Greeks are mortal, and the deductive inference is revealing that information explicitly. So, deduction is a very powerful tool, but it doesn't get us very far in terms of beliefs about the world. The vast majority of our beliefs about the world are formed through induction. And here I'm using the term induction to refer to any kind of ampliative inference. That is, an inference where the conclusion gives us more information beyond what is already implicitly contained in the premises. For instance, every time I have drunk water from this tap, it has been potable, so the next time I drink water from this tap, it will be potable. Induction is crucial for our ability to get by in the world. We have to form expectations about the future in order to act. Imagine if you just had no idea at all about whether the water in your cup would quench your thirst or poison you. This is the capacity to make inductive inferences seems like a very important capacity. Now, unlike deductive arguments, inductive arguments do not guarantee the truth of their conclusions. The best we can do with an inductive argument is show that the conclusion is probable, or that it is justified to believe, or that it's rationally acceptable, or something like that. But since an inductive inference takes us beyond what is given in the premises, then it's always going to be possible for the premises to be true and the conclusion false. It can be true that every cup of water from the tap so far has quenched my thirst very nicely, but the next cup of water might poison me, right? That can be true. That could happen. So, even so, many philosophers have thought that there are inductively strong argument forms, right? Like some inductive arguments are good and some are bad, And the thought is that in the same way as we can specify forms of argument that are deductively valid, so forms of argument where the truth of the premises guarantees the truth of the conclusion, similarly there are certain forms of argument where the truth of the premises will make the conclusion probable, or make the conclusion rationally acceptable. So a standard example is enumerative induction. All observed Fs have been Gs, so all Fs are Gs. All observed swans have been white, so all swans are right. Or all observed Fs have been Gs, so the next F will be G. All observed swans have been white, so the next observed swan will be white. It occurs to me that I made an error in making this particular slide because I've just copied the one inductive form twice. So one of those should say all observed f's have been g's, so the next observed f will be g. But yes, hopefully you get the point. Obviously, the truth of the premise doesn't guarantee the truth of the conclusion, but the hope is that the truth of the premise makes probable the truth of the conclusion. And so philosophers have tried to uncover the rules of induction, analogous to the rules of deduction. These inductive rules should hold universally. So just as you can substitute any concepts into a deductive argument, so it is with an inductive argument. You can substitute whatever you like for f and g. Consider, all observed planets have been made of cheese, so all planets are made of cheese. Again, a silly argument because the premise is obviously false, but the thought is, well, yeah, that would, like, if we did observe loads and loads of planets, all of them made of cheese, then, it would be a legitimate inductive inference. That it would be a legitimate inductive inference that they're all made of cheese. Legitimate inductive inferences are those inferences that have the correct form, that conform to the appropriate inductive rules, just as legitimate deductive inferences are those that conform to the appropriate deductive rules. Now, there are two projects associated with induction in philosophy. Very, very broadly speaking here. There's the descriptive project and the justificatory project. The descriptive project has the goal of trying to articulate what inductive inference rules we actually use. What are the rules of induction? The justification project asks what it is that justifies these rules. So there are a variety of skeptical challenges to induction, most famously Hume's problem of induction. I have a video on Hume's problem of induction that you should check out. I assume that if you're watching this, I'm assuming a little background familiarity with induction. So if you don't know what Hume's problem is, you should definitely go and read up on it or check out my video on Hume's problem. Now, of course, there is no agreed solution to Hume's problem, and in the context of skeptical challenges like Hume's problem, the descriptive project seems to have less importance because Hume's problem and many other skeptical challenges will arise no matter what the rules of induction are. So no matter what we take the rules to be exactly, you can raise the Humean challenge. But it is worth noting that even the descriptive project has largely been a failure. There is no consensus whatsoever about even the most basic inductive rules. For instance, earlier I gave the example of enumerative induction, and this is a kind of rule that is often used in illustrating inductive inference, but it's very questionable whether we actually do use this rule, generally speaking. It licenses a variety of really stupid inferences. All observed f's are g's, therefore all f's are g's. Well, Verity's height has increased each year so far, so Verity's height will increase next year. Or imagine astronomers of the past inferring, the orbital period of all observed planets is less than 100 years, so the orbital period of the next observed planet will be less than 100 years. Or all past winters have been snowy, therefore the next winter will be snowy. Well, in a world of climate change, that's a pretty bad inference. It turns out that actually the vast majority of substitutions that you make into the form all observed f's have been g's, therefore the next observed f will be g, the vast majority of substitutions into that form are really just bad arguments. Now, obviously, philosophers have made more sophisticated proposals about what the inductive rules might be. There are Mills methods, there's hypothetico-deductivism, there's inference to the best explanation, there's Bayesian approaches. All of these are very controversial, and there's often a lot of debate about the most basic features of these approaches. I discussed a lot of these in my Philosophy of Science series, but the point is, there isn't really any agreement on what the inductive rules are. In the case of deduction, by contrast, we have long ago achieved a consensus on a variety of deductive inference rules. The Aristotelian deductive syllogisms are still recognised as valid schemas to this day. Then we have the development of propositional logic, and then we built on that with predicate logic, and then modal logics, three-valued logics, and so on. There is firm and widespread agreement on the basic valid argument forms. There is some disagreement, certainly, but there's a significant amount of consensus. We've now developed formal logical theories of remarkable power, and yeah, as I say, there's a great deal of consensus about this, about which inference schemas are deductively valid. So our theories of induction seem hopelessly primitive by comparison. Now, according to John Norton, the mistake here is in thinking of induction as involving the application of universal rules of inference. The material theory of induction holds that there are no rules of induction, right? There are no formal schemas that distinguish the good inductive inferences from the bad inductive inferences. All inductive inferences are licensed by specific facts. As Norton puts it, all induction is local. So a couple of examples will help to illustrate the material theory. Norton asks us to consider two instances of the enumerative schema, some f's are g's, therefore all f's are g's. So these samples of bismuth melt at 271 degrees, therefore all samples of bismuth melt at 271 degrees. These samples of wax melt at 50 degrees, therefore all samples of wax melt at 50 degrees. So in the first case, Norton says this is a pretty strong inference, and we can even imagine that the number of samples measured is quite small. We might suppose that the scientist has measured the melting temperature of just 10 or 11 samples of bismuth, and of course we're assuming that in both of these cases the measurement is reliable, right? So there's very good reason to think that the observed samples do indeed melt at the temperature. So there's good reason to think that the first premise is true. So anyway, yeah, Norton says that the bismuth inference is a strong inductive inference, even though relatively few samples of bismuth might have been observed. In contrast, the wax inference is a weak inference, and that does not provide a good justification to its conclusion. And this is the case even if the scientist has observed hundreds of samples of wax. From the point of view of the formal approach to induction, there is a puzzle here. Both of these are instances of the same type of inductive argument form, but one is justified and the other is not. What explains the difference? Well, Norton says that the difference lies in the facts that we know about these two cases. The bismuth inference is warranted because we know that samples of elements are uniform in their physical properties that are relevant to melting temperature, and bismuth is an element. So bismuth from one factory is going to be the same as bismuth from another, at least, again, with respect to these properties. We make an inductive inference simply on the basis of this fact. And of course, there is no such fact for wax. The underlying physical properties of samples of wax may all be very different, because what we call wax refers to various different mixtures of hydrocarbons. Wax from one factory may be very different from wax from another. So it's not the form of the inference that licenses the induction, right? It's not that the inference is an instance of the general form some f's are g's, therefore all f's are g's. Rather, inferences of that form are applicable in this case, in the bismuth case, because of certain facts of the domain. When we are dealing with physical properties of elements, we can apply this inference form because of the fact that physical properties of elements are uniform. This is what licenses the inference from one sample to all. Now, I should note there are complications here. In claiming that samples of elements are uniform with respect to melting temperature, that does ignore that some elements have different allotropic forms, which have different melting points. But of course, in any inductive inference, we're taking a risk. So in making the generalization about bismuth, we put aside the possibility of allotropy. Here's a second example. A chemist prepares a new salt of a metal and reports the crystalline form of the salt. Well, this will involve an inductive inference, insofar as the chemist will take the report not simply as describing the form of her particular sample of the salt, but as describing the crystalline form of the salt in general. She makes a fairly immediate inductive inference from perhaps just one sample to all samples. As Norton argues, this was the inference made by Marie Curie in her report on the properties of radium chloride crystals. Curie found that crystals of radium chloride are very similar to those of barium chloride. They have they're elongated needles, they show double refraction, they are colourless, and in particular the crystalline form of radium chloride is isomorphic to the crystalline form of barium chloride. Both have a monoclinic crystal structure. And Curie, in giving the report on her samples of radium chloride, Curie made a fairly immediate inductive inference. She inferred that radium chloride in general has a monoclinic crystal structure. But the radium chloride that she had was prepared only in minuscule amounts. Several tons of uranium ore are required to prepare just a few tenths of a gram of radium. So in this case, scientists observed very few samples of radium chloride, but they made an inductive generalization to the nature of all radium chloride. And what's more, when you read about this case, it will probably strike you as a perfectly reasonable generalization. It's a strong inductive inference despite the tiny inductive base. So, if we state it formally, Curie's inference was a few F's are G's, therefore all F's are G's. Or maybe even just, one F is G, therefore all F's are G's. This sample of radium chloride is monoclinic, so all samples of radium chloride are monoclinic. In general, of course, that would be a terrible inference. It's only acceptable when we substitute the right things for F and G. What made Curie's inference legitimate was her background knowledge of crystal structure. So, generally, instances of every crystal-forming substance will fit into a single characteristic crystallographic system. The crystals will have different shapes, but these shapes will all instantiate a more abstract form. The 7 different forms are shown here, or the 7 different systems are shown here. So in this scheme, crystals are categorized into forms on the basis of the axes characteristic of their shape. Now, for each substance, its crystals will be in one of these 7 systems. And this happens because for every substance that forms crystals, the crystals are built up from repeating unit cells, collections of atoms that have the same shape. So the crystal shown on the left here has a cubic form. It's constructed from many cubes stacked together. The form of the crystal is determined by the shape of its unit cells, and generally each crystal forming substance is based on the same unit cells. Okay, so obviously not just any crystal properties can be substituted for G. Indeed, not just any shape properties can be substituted for G. We may find that a crystal of a salt is a perfect cube, but we wouldn't infer that all crystals of that salt must be perfect cubes. Rather, we would infer that all crystals of that salt are part of the cubic crystallographic system. And those need not be perfect cubes. The vast majority of them will not be perfect cubes. But anyway, it was the background knowledge of crystal structure that allowed Curie to infer that all samples of radium chloride have monoclinic crystal structure. This inference was not totally secure because we sometimes find polymorphism, where the same substance produces different crystalline forms. So the main risk of Curie's inference was the possibility of polymorphism. This risk was reduced for Curie, though, because radium chloride was observed to have very similar chemical properties to barium chloride, and no such polymorphism was observed in barium chloride. Okay, so Norton says that a particular induction is licensed by a fact, and this fact he calls a material postulate. So a material postulate is just a specific fact. The material postulate in the bismuth case is that it is the fact that samples of elements are uniform in their underlying physical properties. This licenses the induction from the melting temperature of observed samples to the melting temperature of bismuth in general. The material postulate of Curie's inference was that crystals of particular substances generally instantiate the same crystallographic system, and perhaps also that radium chloride and barium chloride are chemically analogous. So yeah, the material postulate of an induction is the fact that licenses the induction. According to the material theory of induction, once you have cited the facts that license an induction, that's all there is to say about induction. There are no general rules, only particular facts that license particular inferences. When we ask, why was Curie's inference justified, we should answer this not by showing how it instantiates some abstract universal rule, but rather by simply displaying the facts on which the inference was grounded. And it's the same for all other inductive inferences. I believe that the next time I'm thirsty, drinking water will quench my thirst, not poison me. Why do I believe this? Well, because I know that the tap water in my country is well regulated, so will have pretty much the same chemical properties as it has had in the past, and I know that there's a kind of stability in biological organisms such that, the biology of organisms doesn't constantly change, so that a substance that's fine one day will poison you the next. So like that's it, right? That's what licenses the induction, that when I take a sip of this water here, which I just did, it will quench my thirst, not poison me. Of course, that judgment in itself is not controversial. What's controversial is that according to the material theory, there is nothing more to say about induction, right? Like my inductive inference that the water will quench my thirst is not based on any general rule. It's just based on the fact, the specific facts. Okay. So there are a few general arguments for the material theory given by Norton. First, there is the failure of proposed universal rules. No attempt to describe the rules that we supposedly use has succeeded. There is no agreement even on what the most basic inductive rules are. And this, of course, raises the question, if we use universal rules of induction, why is it so hard to state them? This isn't a problem, or at least isn't anywhere near as much of a problem for rules of deduction, as we have seen. Now, obviously, there isn't really time in this video to explore this point in detail. Going through all of the views of induction would require a whole video series, but I do want to just very quickly look at two popular contemporary proposals, just to help, illustrate the sort of line the material theory takes. On the material theory, right, that there is something to be gained by thinking about inductive rules. The key point is that these rules are only applicable locally, right? You can apply certain formal rules only when the relevant background facts are in place to license them. So in the previous discussion, we've already noted that enumerative induction fails as a general rule, but in specific circumstances, like Curie's inference, it's applicable. So yeah, a couple of other proposals for inductive rules. Well, a popular proposal is inference to the best explanation. In inference to the best explanation, we propose a variety of theories for some phenomena, and then we judge those theories against a range of explanatory virtues. Empirical adequacy, consistency, simplicity, explanatory scope, fruitfulness for further research, and so on. The theory that performs best against these standards, the theory that conforms best with the evidence, that is simplest, that solves the widest range of problems, is then inferred to be true. Inference to the best explanation has been proposed as a general schema for induction. It accounts for enumerative induction in the cases where enumerative induction works. So from all observed f's are g's, we can infer all f's are g's, just in case this conclusion is the best explanation for the premise. So that is, there are circumstances where the best explanation for the pattern in our observations is that some broader pattern obtains. The best explanation for the uniformity in observed melting points of bismuth is a general uniformity in the melting point of bismuth. By contrast with something like all observed swans are white, well, if we've only observed swans in one country, then the best explanation for this is not that all swans are white, because, well, we know that there are differences in species colours in different places. Inference to the best explanation is one proposal, one contemporary proposal for what might be a sort of foundational or universal inductive rule. Now, it's certainly possible to interpret many of our inductive inferences as inferences to the best explanation. But we might worry that the reason for this is simply that inference to the best explanation is so vague. What exactly is an explanation, and what are the standards by which one explanation is judged to be better than another? It turns out there's a huge debate about this among philosophers of science, and it seems to be highly context dependent. There really isn't a consensus about even concerning what explanation is, let alone what makes one explanation better. Some explanations involve subsumption under a law, some explanations cite causal processes, some explanations proceed by unifying disparate phenomena. Different philosophers will have different views on whether these count as legitimate explanations, and even if they do count as legitimate explanations, how we can tell whether one is better than another. So unfortunately, if this is an inductive rule, it certainly hasn't been articulated in a way that has achieved any kind of consensus or precision. So now Norton is skeptical that scientists actually appeal to explanation in many cases when trying to show that a theory is superior to its rivals, or at least where they do appeal to explanation. Norton thinks that this is basically just a disguised appeal to specific local facts. So when a scientist is trying to show that a theory is superior to its rivals, Norton says that usually proceeds by trying to show one of two things. First, the scientist might try to show that the available evidence contradicts one of the rivals, given the shared auxiliary assumptions. For example, Newtonian mechanics is contradicted by the precession of Mercury's perihelion. At least by the value that took. Newtonian mechanics was never worked out in such a way that it could accommodate that evidence. So when general relativity was proposed and did accommodate the evidence, well, it was immediately preferred for that reason. Second, scientists will try to show that the rivals involve contentious assumptions for which no evidence exists. In this respect, the rivals have an evidential debt. Norton gives the example of Charles Lyell's argument for uniformitarianism. According to the uniformitarian, geological features are products of the same types of causes that we observe today, operating over millions of years. This contrasts with catastrophism, which treats many geological features as products of cataclysms that very, very rarely occur. Now, Lyell's theory rested on two claims, according to Norton. First, and I quote, "It is possible that present geological features arose over long periods of time from causes now operating." So there's a possibility claim there, right? Like it's possible that this was the case. And secondly, and I quote, "It is unlikely that any other admissible account can accommodate their origin." So the justification for the second claim is that the catastrophist account it must engage in speculation, right? Like it must just speculate that there are causes which at the time would have been unknown, or that there were known causes but of unknown intensity. So, the catastrophist would have to suppose that, like maybe there was some cataclysm in the earth of a kind that has never been observed, or that maybe processes like earthquakes and erosion that we currently observe happened in the past with much greater intensity. And of course, there's no direct evidence for such causes, or at least there wasn't at the time that Lyell was writing. We actually do have evidence for things like that now with asteroid impacts, but at the time that Lyell was writing, there was no direct evidence for these cataclysmic events. So the only reason to postulate them would be due to a prior commitment to the catastrophist theory. So catastrophism has an evidential debt relative to uniformitarianism. Now, we can frame all of this in terms of general relativity and uniformitarianism providing a better explanation of the relevant phenomena. But I think what Norton would say is, well, look, this is just this is vague. It doesn't tell us anything substantive, and it actually obscures because it's so vague, right? It ends up kind of obscuring the arguments that scientists are actually making, right? General relativity was preferred because the evidence contradicted its rival. Uniformitarianism was preferred because the catastrophist invoked assumptions for which no evidence exists. In neither case do we need to frame that in terms of explanation, or like in terms of one providing a better explanation. It's simply that one theory is better in accord with the empirical evidence. In any case, what counts as the best explanation will simply be determined by background facts. So we haven't really escaped the point that inductions are licensed by specific facts. Norton gives the example of a study on the healing power of prayer. Suppose that this study finds an apparent positive result. where this is like a statistically significant positive result? Well, a theist would take the best explanation of this to be divine intervention. An atheist, by contrast, would suggest perhaps that there is a methodological flaw in the study, or that maybe there's some sort of common cause, like maybe people who are religious have some other reason why they end up like maybe there's just a placebo or something like that, or maybe it's just a coincidence, right? After all, if you run enough studies on prayer, a few of them will find positive results just by chance. Certainly the atheist will not see divine intervention as a good explanation, and the difference in judgments here lies in the difference in their beliefs about the background facts. If we assume that God exists, and we assume that he is intervening in the world in various ways and responding to his followers when they are in need and so on, then we will naturally apply the same explanation to a study showing that the recipients of prayer tend to have better health outcomes. So what we take to be the facts of a particular domain constrain what counts as a good explanation for phenomena in that domain. So that's one popular approach. Norton thinks that the material theory is better than it. Another popular approach is Bayesianism. Bayesianism is based on formal probability theory. The basic idea of Bayesianism is that some evidence confirms a hypothesis just in case the evidence raises the probability of the hypothesis. So the probability of the hypothesis given the evidence is greater than the initial probability of the hypothesis. We call the probability of H the prior probability of H, and the probability of H given E the posterior probability of H. Now, we can work out the probability of H given E using Bayes' theorem. Bayes' theorem is derived from the axioms of probability theory, and it says the posterior probability equals the probability of E given H multiplied by the prior probability divided by the probability of E. Okay, so suppose I'm, that as part of a routine medical test, I'm given a HIV test. So, routine medical exam, I'm given a HIV test, and the test comes back positive. Now, assume that the HIV test has a 1% false negative rate, so 1% of people who do have HIV will have a negative result, and it has a 2% false positive rate. So 2% of people without HIV get a positive result. Our question is, what is the probability that I have HIV given that I've just had a positive result on this test? Well, we can use Bayes' theorem to work this out. So for the probability of E given H, the probability that I have a positive result on the test given that I have HIV, we can see that this is 0.99, right? The test has a 1% false negative rate. That means if 100 people with HIV are given the test, 99 of them will test positive. For the prior probability that I have HIV, we can take the prevalence of HIV in a population of people like me, right? I live in the UK where HIV isn't all that common. I'm not in a high-risk group because, I don't inject heroin. I don't frequently engage in promiscuous, unprotected sex. I don't know the exact numbers here, but let's just say that 0.1% of people relevantly like me have HIV. So the prior probability that I have HIV is 0.001. For the prior probability of a positive result, well, we know the general prevalence of HIV, and we know the false negative rate and false positive rate of the test, and we can work out the prior probability of a positive result from this. 0.1% of people are HIV positive, 99% of them get a positive result, 99.9% of people are HIV negative, and 2% of them get a positive result. And this allows us to calculate the overall probability of a positive result on any given test. So anyway, we've got some numbers here, and we plug these numbers into Bayes' theorem, and it turns out that the probability that I have HIV, given a positive result on the HIV test, is approximately 0.047. Good news for me, I don't really have anything to worry about. The posterior probability that I have HIV is higher than the prior probability, so the positive result does provide some confirmation to the hypothesis, but still, I probably don't have HIV. On the other hand, if I were to take 3 of these tests, say, and they all gave a positive result, well, in that case, the probability that I have HIV would be pretty high. So, Yeah, so yeah, this is an illustration of how Bayes' theorem works, right? We get the numbers, we plug them into Bayes' theorem, and this tells us how to update our beliefs in response to evidence. Now, Bayesianism provides a very powerful tool in contexts like medical testing, but the idea of Bayesianism as a general epistemology is that we can extend the same framework to reasoning and, in particular, scientific theory testing in general. So you just need to specify the hypothesis, specify the evidence, get the probabilities of the various elements, and then plug in the numbers. Easy, right? Like, you've got Bayes' theorem, it's just a matter of, specifying what the hypotheses are, what the evidence is, and then plugging in the numbers. Of course, the big question for the Bayesian is, where do we get those numbers from? So what, in general, is the prior probability of a particular scientific hypothesis? What, for example, is the prior probability of punctuated equilibrium as a theory of macroevolutionary change? Or what is the prior probability of the Big Bang model? Well, it's not entirely obvious how we even begin determining these prior probabilities. Like, I can ask, what's the prior probability that I have HIV? And I can take, the reference population as the population of the UK, and I can look at the behaviours I engage in, and that gives you some reasonable place to start in terms of working out what the prior probability that I have HIV would be. But when we're dealing with a scientific theory, I mean, it's not. I don't know. I mean, where do you even start, right? Where the prior probability of the Big Bang model, it's not clear where you even begin. We have the same problem when we ask for the probability of the evidence that we might get for a particular hypothesis. So what was the probability of the detection of cosmic microwave background radiation before that detection was made? I mean, again, where do we begin? So to work this out, we would need to know the probability of cosmic microwave background given that the Big Bang occurred, and the probability of cosmic microwave background given that the Big Bang did not occur. And the obvious problem here is, so first of all, the first probability, that depends on what auxiliary assumptions we adopt. There may have been a Big Bang, but then some other process caused the extinction of the cosmic background radiation. I don't know, maybe a universe in which photons decay over time or something like that. But so there could have been some other process, right? Even with a Big Bang, there could have been some other process that meant that there was no cosmic background radiation. So the probability of observing cosmic microwave background radiation given that there was a Big Bang, I mean, it's not, again, it just depends on what auxiliary assumptions you adopt. The second probability is even more problematic because not Big Bang that's just a catch-all for all the hypotheses other than the Big Bang model, and there's an infinite number of those. On some of those hypotheses we might expect cosmic microwave background radiation, on others we would not, and of course all of that would depend on the auxiliary assumptions that we make. So a general concern about Bayesianism is that it involves simply pulling probabilities out of thin air. Moreover, according to Norton, approaches like Bayesianism tend to commit the fallacy of spurious precision. Many inductive inferences are imprecise. We talk of an inference as being weak, reliable, strong, nearly certain, whatever. But often we can't attach a precise mathematical value to the strength of the inference. Indeed, often there isn't even really any common measure to compare the strengths of inductive inferences in different fields. Try to compare a strong inference concerning crystallography, such as Curie's generalization from a few samples of radium chloride et al., with a strong inference in astronomy, such as the inference to the Big Bang theory from observations such as galactic redshift and cosmic microwave background radiation. I mean, those were both strong inductive inferences, or at least many people would consider them strong inductive inferences. But there isn't kind of some common number that can be put on both of them. There are specific situations in which the use of mathematical probability theory is reasonable. If we toss a fair coin 10 times, right, then you can work out the probability of getting at least one head, and that will be an extremely precise value. I mean, that value will be based on certain background knowledge, such as that the coin is perfectly fair and that a fair coin is a coin that lands heads exactly 50% of the time. Sometimes in the sciences, background facts do authorise the use of probability to measure inductive strength. So consider cases like radioactive decay, DNA forensics, genetic inheritance, games of chance in casinos. The background facts, such as facts about physical laws or facts about the mechanisms of biological inheritance, allow the application of probability theory. But we can't do, the background facts don't license this in the case of Curie's induction. Indeed, in Curie's case, there may not have even been a prior probability at all. So the hypothesis here is radium chloride has monoclinic crystal structure. Prior to the observation of samples of radium chloride, scientists might simply have been totally non-committal about this hypothesis. They might have refrained from attributing any particular probability to it. And Bayes' theorem can do nothing with vague probabilities, right? In order to apply Bayes' theorem, you need to actually specify what the prior probability is. So, this has been very, very quick. I have videos on Bayesian epistemology if you want more detail here. And obviously there are responses from the Bayesian. I'm just trying to give a flavour of the problems for proposed inductive rules. And so the message of the material theory is that inductive rules, so it's yes, right, they can be useful, but they're useful only when the relevant factual background conditions have been specified and are such as to license the application of those rules. So yes, there are cases, right, where Bayes' theorem is a very powerful tool, but it can't be applied just in general to like inductive inference in general. It can't be applied to scientific reasoning in general. That's the message. So one issue then that favours the material theory is that the formal approach has been a failure. Nobody seems to be able to say what the rules are that we use, let alone provide the justification for them. The second argument for the material theory is that unlike formal approaches to induction, it accommodates the data easily. The difference between what we intuitively recognise as good and bad inferences is readily explained by the material theory, as we saw in the bismuth and wax example. The material theory directs us to look at the facts that license the induction. Moreover, the material theory is more in line with actual scientific practice. An important aspect of scientific practice is control of inductive risk. Science is built on induction, on inferring to theories and models beyond the immediate evidence. And obviously, scientists want to minimise inductive risk, or at least they want to be as precise as possible about what the risks of a given inductive inference are. Every scientist knows that no hypothesis can be asserted with certainty, but some seem to be better established than others. And we should try to identify factors that might lead us astray, right? So, we want to control inductive risk. This is a really important aspect of the scientific enterprise. Now, from the point of view of a formal approach to induction, there will be two steps to reducing inductive risk. First of all, we need to gather as much evidence as possible. The more observations we make, the stronger will be the inferences on the basis of those observations. That's an obvious point. Second, we must expand our collection of inductive rules. I mean, this is just what we do with deduction. We search for the valid deductive rules, Aristotle's syllogisms, then propositional logic, then modal logic, and for each area of discourse, we try to find the deductive rules that govern it. Deontic logic and various other logics of obligation and so on, temporal logic, three-valued logic. We develop all of these deductive rules in lots of different areas, and as we amass more and more deductive rules, our deductive abilities improve. So similarly, we should try to expand the inductive inference schemas available, and we need to say something about the reliability of these schemas. We might say, one inductive schema is the enumerative schema that from all observed f's or g's you infer all f's or g's, and then you say something about how reliable it is based on how many observations are made. Presumably an enumerative induction is going to be more reliable with more observations. Now here's the surprising fact. Despite the fact that empirical science is an inductive enterprise, and that scientists are concerned with reducing inductive risk, scientists pretty much never try to develop our catalogue of inductive schemas, with the possible exception of work in sciences like statistics. But somebody can be a very successful scientist and yet make no contribution whatsoever to the articulation and justification of general inductive rules. I'm reminded of the famous comment from C.D. Broad that induction is the glory of science and the scandal of philosophy. Scientists just get on with making inductive inferences, and they seem to be really good at it. Or at least they seem to be as good at it as anybody else, as anybody can hope to be. But the point is, right, like the inductive inferences that are made in science have given us theories of remarkable power and scope. Scientists just get on with making inductive inferences without stating what rules they are following. It's only philosophers who seem to be concerned about articulating what the inductive rules are. You don't tend to find physicists and biologists worrying about what exactly counts as an explanation, or the rules for what makes one explanation better than another. You don't find them trying to force all their inferences into the Bayesian formula. Not to say that they never do that, sometimes they do. But it's in limited contexts. So if there are universal inductive rules, analogous to the deductive rules, it's a bit strange that the people who are the best at doing induction, the people who spend their lives doing induction, don't seem to care about the inductive rules. Now, from the point of view of the material theory, control of inductive risk involves just one step: collecting evidence, working out what the facts are. All inductive schemas are applicable only locally in specific domains, and it is the facts of those domains that license the application of a given schema. So the reason why scientists don't spend their time trying to articulate inductive rules is because they would gain nothing from this, right? All of the benefits come from discovering facts. So the material theory will claim to be more in line with the facts of scientific practice. Third, the material theory has, it is argued, better resources to solve the Humean problem of induction. So, we're all familiar with Hume's problem. What is it that justifies induction? Well, the trouble is that any attempted justification of an inductive rule will be either too strong or it will be circular. So, if you take the inductive rule, all observed f's are g's, so all f's are g's. This obviously can't be justified deductively. It's obviously logically possible that the next f will not be a g. What about inductively? Well, the argument is presumably going to be induction has been successful in the past, so it will be successful in the future. Well, that's plainly circular. We're using an instance of the rule to justify the very rule we want to justify, right? We're using the rule itself. Induction has been successful in the past, so it will be successful in the future, is itself an inductive inference. Now, the usual way around the problem of induction has been to appeal to a universal warranting fact, something like the principle of the uniformity of nature. The uniformity principle says something along the lines of the future will be like the past, or nature is uniform, or something like that. Now, the idea then is that if we take the uniformity principle to be true, then we can be assured that induction will be reliable. The fact that all observed instances of water have quenched my thirst, in conjunction with the general fact that the future will be like the past, justifies my belief that the next cup of water will quench my thirst. So, look, every philosopher accepts that inductive inference is not as secure as deductive inference, but also it's not universally applicable in the same way. Valid deductive inferences are valid no matter what the world is like. But there are some worlds that are more or less hospitable to induction. For any inductive inference, there are worlds in which it can fail. Curie's inductive generalization concerning the crystal structure of radium chloride would have been a bad inference in worlds where substances did not tend to form common crystal structures. Now, the traditional approach to the skeptical problem of induction is to try to find a general fact about our world that holds in all domains, that licenses the use of inductive rules. Provided the uniformity principle is true of our world, provided it's true that the future will be like the past, or that nature is uniform, then the thought is we can rely on induction. So as Mill puts it, and I quote, John Stuart Mill, I quote, The proposition that nature is uniform is the fundamental principle or the general axiom of induction. In order for our inductive inferences to be justified, in order for us to rely on induction, right, we have to make the assumption, it has to be the case that nature is uniform, or the future will be like the past, that some sort of uniformity principle holds. The question, of course, is what justifies the belief in the uniformity principle? And here we have the kind of classic problem of induction. So all inductive inferences presuppose the uniformity principle, but the uniformity principle is not justified deductively, right? I mean, it's logically possible that any given uniformity will fail to obtain in the future, right? It's logically possible that the world would just go completely crazy, like the next second, right? Third, the uniformity principle is not justified inductively. So how would you justify the claim that the future is like the past, or that nature is uniform? Well, that justification would itself have to be so if that justification is inductive, that would itself have to presuppose the uniformity principle, so it would be circular. No other means of justification is available, so there is no justification for the uniformity principle, so there is no justification for induction. That's one statement of the problem. Now, the material theory rejects the first premise. The material theory rejects the claim that all inductive inferences presuppose the uniformity principle. On the material theory, there is no general principle that underwrites all inductive inferences, because all induction is local, based on specific facts. In a sense, every inductive inference is unique. Each inductive inference is warranted by facts specific to that inference. This is just another way of saying that there are no inductive rules. And the thought is that if you give up on inductive rules, then the Humean problem doesn't really even get started. In any case, even if we could establish the uniformity principle, it wouldn't really help us to understand any particular inductive inference, because the world is uniform only in certain very specific respects. So perhaps certain laws of nature are uniform, or certain properties of natural kinds are uniform. But beyond this, the world is in constant flux. Merely stating the uniformity principle does nothing to help us identify just what the uniformities are. It only tells us that there are some uniformities. So even if we did have a justification for the uniformity principle, it wouldn't be this that powers inductive inferences. Inductions, as the material theory will say, are powered by specific facts. Now, it might be objected that none of this really helps to solve the skeptical problem. Now, there is no way on the material theory of raising a skeptical challenge to rules of induction, because the theory tells us there are no rules of induction. But any specific inductive inference can be challenged. The bismuth inference is warranted by the belief that generally elements are uniform with respect to properties relevant to melting temperature. But what justifies this belief? Right, and then the question is going to be, okay, and what justifies that belief, and so on, right? So have we really solved anything here? Well, according to Norton, there isn't really any significant difficulty here. So, as Norton puts it, and I quote, "We induce a fact with an induction that is grounded by the facts of a material postulate. These latter facts are justified by inductions that are in turn grounded in the facts of other material postulates, and those facts are justified by inductions grounded in other facts, and so on." So basically you have facts grounded in facts, and so on. Now, this does leave us with a question, certainly. It leaves us with the question of how these chains of justification terminate. And that's an important question, and one can raise skeptical issues here. But this isn't the problem of induction. This is a much more general problem of justification. Specifically, it's Agrippa's trilemma. So there are three alternatives for the structure of justification. Either chains of justification terminate in foundational beliefs that do not themselves have any justification, or chains of justification are circular, or chains of justification go on in an infinite regress. All of these options are problematic in fairly obvious ways. But this is a general problem of justification. It's not the problem of induction. I mean, this same problem would arise for the attempt to justify deductive rules, for instance. Right? I mean, so this problem is going to arise for any belief that you have, not just beliefs that are formed through induction. So this is not the problem. So the problem that the material theory faces is just the general problem of justification that all beliefs face. It's a general problem of justification in general, right? It's not the specific problem of induction. So on the formal theory on formal approaches to induction, right, induction can't be justified deductively, and an inductive justification would be circular. On the material theory, inductive inferences are warranted by facts. The warranting fact is not usually justified deductively. Is it justified inductively? Well, yes, but the defender of the material theory will say there's not any kind of problematic circularity here because the warranting fact is distinct from the conclusion. We're not like using induction to justify induction. We're using one fact to justify a distinct fact. So on the formal theory, on the formal approach, we have an inductive rule which is justified by the uniformity principle, but the uniformity principle itself can be justified only by an inductive rule. On the material theory, we simply have two distinct facts. So we have the fact, all bismuth melts at 271 degrees. That's justified by our observations of bismuth and by the fact, right? The material postulate is the fact that generally chemical elements are uniform in their physical properties. So we have this fact. Chemical elements are uniform in their physical properties. And the justification for this belief about chemical elements is going to be some other distinct fact. You'd appeal to previously established facts in chemistry. So we just have this chain of distinct facts. Now notice how, again, this is how scientific practice seems to work, right? Like, no scientist cares about answering Hume's problem of induction. If a particular inductive inference is queried, a scientist will respond by citing the facts that license the inference. And there is going to be a kind of regress here. When we ask for the justification of a material postulate, other facts will be cited, and then we can ask for the justification of those facts. But there's nothing fanciful about this. This is just going to be a matter of basically articulating the history of science, right? Or, I suppose, more likely, articulating a streamlined account of evidential support relations in science of the kind that can be found in science textbooks. When you make when you state some scientific fact and somebody asks you what the justification for that is, you state some other fact established by science, they ask you for the justification of that, you can state some other fact. I mean, just as is done in scientific textbooks. So the claim will be, well, the material theory of induction doesn't face the problem of induction, and that is a significant point in its favour, if that is true. If it is true that it avoids Hume's problem of induction, that's a big point for the material theory. Okay, I just want to turn to one objection here. So even if the material theory does solve Hume's problem of induction, we might worry that it in a way raises a new problem. So inductive inferences are licensed by facts. Now, when Norton illustrates his thesis, he appeals to examples in which people have a significant amount of relevant background knowledge. Marie Curie had knowledge of crystal structures. But on the usual philosophical approach to induction, these kinds of cases where people have a lot of background knowledge, just obscure the problem. So I think that what the sort of usual line would be is we really need to consider cases where this kind of background information isn't available. Because the question, after all, is going to be, well, how do we gain all that background information in the first place? How do we arrive at all of those beliefs? How do we arrive at those material postulates that license inductions? And, I mean, this is important because it's not simply that inductions are licensed by facts. Inductions have to be licensed by known facts. The fact about crystal structure would have been useless to Curie if she had no awareness of it. So this is what Thomas Kelly in his article Induction Without Rules calls the prior knowledge commitment of the material theory. Learning a fact by induction requires prior knowledge of the material postulate that licenses the induction. Now, this raises two closely related problems for the material theory. First, there is so I guess actually this is there are two sort of forms of the same objection, right? So one way to make this objection is as a historical objection, and this is suggested by Thomas Kelly. And so this is just the question of, well, okay, like, how did humanity actually develop this inductive knowledge? In particular, how do we make the very first inference? You can imagine tracing back the practice of making inductive inferences, and then we come to the moment of the very first induction. Now, consider the case before anybody has ever made an inductive inference. Call the totality of non-inductive knowledge N. Presumably, N will consist of propositions about brute experience plus deductive consequences of those. The question is, how do you make any inference beyond N? And the concern here is, there's just nothing in our experience to play the role of the material postulate. From claims only about one's own experience, you can't get anywhere. Without knowledge of a more general scope, your own experience will tell you only about your own experience. So yeah, there's just no way, right? Once you from the non-inductive knowledge, from the non-inductive base, there is no material postulate that will license an induction. So there's no way for the induction to get started. Well, Norton responds that this scenario is an idealization. Obviously we don't have any detailed idea what the cognitive processes were like in our ancestors, but it seems very unlikely that there was a point where they actually held only non-inductive beliefs. Every human society, including societies that existed before modern humans even evolved, actually, would hold a variety of general beliefs about the world. Plenty of these beliefs would have been unjustified, but that's where we start from, right? We don't start from like brute experience plus deduction. We just start from this variety of general beliefs. Indeed, it's unlikely that our distant ancestors would even have made a distinction between deductive and inductive inference, or would have thought very deeply about the appropriate methods of belief formation. They would have formed beliefs through perception, speculation, tradition, authority, memory, testimony, rituals like the chicken oracle, and so on. By the time people actually formulated the distinction between deduction and induction, they would already have held a host of beliefs about the world that could license further inductions. Beliefs like humans die when they fall from great heights, or apples are nourishing. It seems likely that evolution would have inculcated certain general tendencies in us towards particular beliefs, such as the danger of heights will have tended to produce the belief that humans die when they fall from great heights. Many of these beliefs about the world would have been held without justification, but again, the point is, once you've got beliefs about the world, you can use them as material postulates in inductions. Okay, so second way to put this prior knowledge problem is in terms of justification. So we might say, look, the historical story is illustrative, but that's all. The fundamental problem for the material theory concerns the support relations of our present knowledge. Empirical knowledge is grounded in experience, but in experience alone, there is no material postulate that can license the inductive inference to any generality beyond immediate experience. Right? There is nothing that can license the inference to any claim about the independent world. And moreover, even if we reject empiricism and we hold that we have synthetic a priori knowledge of some sort, well, we've already seen that, according to the material theory, inductions are licensed by local facts. So the synthetic a priori might give us a principle such as the uniformity of nature, but surely it's not going to tell us that, in general, every crystalline substance has a single characteristic crystal form. So the material theory fails to account for how we can justifiably infer beyond experience. Yes, people do infer beyond experience, but on the material theory, there are no grounds on which this can be justified, because experience alone just doesn't provide us with the right material postulates. So Norton makes a couple of points in response to this. First of all, he says that the objection rests on the assumption that we can strictly demarcate experiential knowledge from the rest of our knowledge, that we can have a set of beliefs that just express the content of our experience. And he denies this. He says there is no set of propositions that express merely the content of experience alone. Propositions about experience are understood in terms of the world that is experienced. Norton gives the example of the ball is red. This is a straightforward observation report, but this involves an appeal to the concept ball and the concept red. A ball is a spherical object which may be rigid or elastic and which can roll if pushed with enough force. So in talking about balls, we need a general understanding of geometry, of the elastic properties of materials, of dynamical motions. I mean, in like when we say like the ball is red, we're already kind of assuming that there is some object there of a particular shape, right, that behaves in particular ways. Similarly, appropriate application of the concept red requires the ability to classify a range of colours. It's learned by engaging with a range of external objects. A person cannot understand what the term red means if they couldn't properly distinguish a red object from a pink object. So in identifying something as a red ball, we have to locate it in the space of a more general theory about not just ourselves but also the world. And you know, we will find the same kind of problem, Norton thinks, in any proposition we try to form that is just about experience alone. More generally, Norton's view is that justificatory relations between beliefs are not structured in a simple hierarchical form. So, according to Norton, it's not that we have propositions about brute experience at the lowest fundamental level, and then we build up from experience bit by bit, where facts at a higher level are inductively licensed by those at a lower level. Norton favours something more like a kind of coherentist view. In practice, he says, we can proceed by making suppositions. So we can forward a proposition that doesn't have any justification. We can forward it just provisionally as a starting point. So we can assume it to state a fact and then use this to license inductive inferences. And we then have to return to our supposition later once we have a whole set of other beliefs in place, and we can then use some of these other beliefs to provide support to the initial supposition. Norton says, and I quote, "We end up with a structure in which every warranting fact is supported by other inductive inferences in a highly connected, massively tangled structure." For example, we make an inductive inference from the observed positions of Venus to the claim that Venus has an elliptical orbit. Obviously, there will always be countless ways of drawing the line on the observed positions of Venus, but we infer from those observed positions to an elliptical orbit. And part of the warrant for inferring an elliptical orbit is Newton's inverse square law of gravity, plus certain general facts about the structure of the solar system, such as that the vast majority of the mass of the system is in the sun. These facts support the claim that planets orbit in ellipses. However, Newton's law itself gains inductive support partly from the elliptical orbits of the planets. There are many reasons for taking the planets to orbit in ellipses, one of which is Newton's law. And the more planets we find that orbit in ellipses, the stronger the support will grow for Newton's law. So as we make more and more observations of Venus, which provide more support for the elliptical orbit, this can then feed back, as it were, and provide support for Newton's law. This is even though Newton's law was one of the facts that initially licensed the inductive inference to the elliptical orbit of Venus. That's obviously a very simplified example. There are going to be lots of different reasons to favour Newton's law and lots of different reasons for taking the orbit of Venus to be elliptical. So knowledge is structured not like a tower where we build up gradually from foundations. Norton says knowledge is more like an elaborate stone arch, where each of the stones in the arch gains support from the stones around it, both stones above and below. You can't build an arch by simply stacking stones one on top of the other. Similarly, in science, propositions about experience form the bedrock, as it were, but the propositions of science are not then just stacked one on top of the other. Support for any given proposition will be based on various other propositions of greater and lesser generality, or more or less close to immediate experience. And the use of provisional hypotheses can be seen as analogous to how we might need scaffolding to build an arch. The provisional hypothesis is a scaffold proposition. We take a bet on it and see if it works and try to use it to draw new inferences. And then we have to return to it later to remove the scaffolding. We do this by showing how it is itself inductively supported by propositions that are now well established. If we can do this, then the initial provisional hypothesis will gain inductive support and just become part of the arch. The scaffolding will be removed. If not, if we can't do this, well, we'll have to reject that hypothesis and try something else. But yeah, so this is Norton's answer to the justificatory problem. Even if we assume that we can have a set of beliefs just about experience, Norton rejects the kind of, he would say, well, the justificatory problem rests on a sort of too naive foundationalist epistemology, which the material theory need not be saddled with. Right. Well, that's what I wanted to talk about. That's the material theory of induction. Hope you found it interesting. Goodbye.